Let's talk now about the basic modeling concepts, basic elements, single and multi-port devices. So the first thing that we're going to do is to look at different variables in different energy domains. Now, what does this mean? It means that if we have, for example, a mechanical system in here where you have a mass and you have this hold on for a second, make sure this is, yeah, if you have a mass here, you apply a force and the mass moves. That's very elementary. If you have a resistor, in this case on this electrical circuit, if you apply a voltage, a current circulates, right? That's, if you have this rotational system where you have this flywheel and then you apply a torque to it, then obviously it's going to be, the result is going to be an angular velocity. So if you have on the one on the right hand side, if you have a let's say a tank in there, this is a hydraulic system, and you fill it, then you're going to create those variables that you see on the bottom. There will be a pressure and a volume flow rate. What is important in this case is that the variable F multiplied by V on a mechanical system is power. The variable V for voltage multiplied by the current I is power also on an electrical system. The model on the lower left that says that T for the torque multiplied by the angular velocity is also power. And then the last one, the volume flow rate multiplied by the pressure, this too is power. I believe that this is the time where you begin to appreciate what Professor Painter did. He looked at this and he said, you know what? All these variables, they are families of variables that essentially perform the same function but in different systems. For example, if you have a force, it's like the voltage on an electrical circuit. But if you have the torque, also is like the voltage. And on a hydraulic system, the pressure is like the voltage or like the force, and the volume flow rate is either like the angular velocity, the velocity, or the current. So then, with this thinking in mind, he says, I don't need all these variables. I need only two variables. Instead of having F, B, V, I, T, W, P, and Q, he says, I am going to replace all this F, B, T, and P by this variable called effort. And then he says, I am going to replace the velocity, the current, the angular velocity, or the volume flow rate by this other variable that I will call flow. So whenever you are looking at a system that has different components in different energy domains, and you talk about efforts and flow, what Painter is saying is that, these variables act together. They interchange energy between each of the elements. But always any pair of these two variables would be power. Okay? So this is part of the fundamentals behind the bond graph modeling technique. So let's just go one more, and then finally make a little table with a summary of what this is. This is force is measuring newtons, and voltage in volts. The torque in newtons meters, pressure in newtons per meter square or kilograms per centimeter square or pounds per square inch. And the flows are the velocity, the current, the angular velocity, and the volume flow rate. So I will replace all these names. Instead of having 8 or 10 of those, I am going to make 2 of those, efforts and flows. Okay. Okay. Then Professor Painter came with this, it's called the tetrahedrons of a state. All right. That actually says that Q is a generalized displacement and P is a generalized momentum. But you know the displacement is, you need to say, okay, the velocity is dx dt, so the displacement would be the integral of the velocity. So that's described here, see? The relationship between F and Q in this case down here, see, you have that F is dq dt, or you could say that Q is the integral of f dt, see? On this other one here, it says that E is dp dt, but you can also put it in the other form, in the integral form, because this is derivative form. Okay. Now, here's another advantage that you can see. You have 1, 2, 3, 4 times 4. So that is 16 different variables. And Peter is saying, no, no, no. Don't do this. Don't do all the 16. Just do this 4. See, with an effort variable, a flow variable, and an integral of this, which is the displacement, and integral of the, on the other, so displacement and momentum. So if you learn about this 4, that's all we need. Okay, any questions about this? It's better to have these 4 variables than to have 16. But that's what effort, flow, and displacement and momentum represent. Now we are going to begin putting together some systems, and just for fun, why don't we just give it some word names? Some names in here, some word bond graphs. Here you have the the battery connected to the starter and to the Bendix to start your car. Do you see now what the idea is? We have this system here with the battery and this motor and this Bendix. So let's just put words. Battery, motor, Bendix, and in the connection, in this pipeline that connects these two, always you will find those two variables, the voltage and the current, or in this case, torque and angular velocity. Hmm? Bendix is just a little gear that engages on the flywheel of the engine in your car and turns it. Looked at this model of an entire vehicle. In an easy way, you can get a model that is not a Mickey Mouse model, it's a significant one. In here you have the engine, and of course the throttle, and then you have the clutch, which is a control switch basically, and then you have this here. And then you have the gearbox, which is also another element that is controlled depending on which speed it is. And then you have the drive shaft in here, and then the differential gear, and then it goes to both wheels like that. That is the model of an entire vehicle. But now you can see we're stepping up. We just don't have two elements. We have a few elements, but we would like to see it that we put together the entire system this way. Okay, so that's how you put together what we call a word bond graph or a junction graph or a connection graph.